Right. Now let's see what is this simple harmonic motion. Right, I'll take people this way. A particle P of mass simple m. This way, a smooth plane. We have particle P is here. Mass is m, right? Particle P is of mass simple m. And suppose here we have a fixed point O. Right, this is the fixed point. Fixed point O, right? Okay. Now, this particle P is acted a force that is always pointing towards the point O like this. Force is F. And suppose the distance from this O to this P is X. Okay. Then this force capital F is proportional to this X. X is the distance from the fixed point O to the particle P. The force capital F acting on this particle P is such that force capital F is proportional to X. Therefore, this proportionality you can replace, and you can write this as an equation. F equals kx, where k is a positive constant. K is a constant. K is a constant. Right. Now, when this particle is projected from the point O, suppose with the particular velocity, say u. Now, what will happen to the particle while it is moving to the right? Yeah. People, now, if there is no force acting on this particle, since the plane is smooth, okay, plane is smooth, the particle moves on the plane with constant velocity, this u, with constant velocity, this u, right? Now, in this case, when the particle tries to move starting from this u to O to right, the force F is acting in the opposite direction. That is to say, people, you know, when we project a particle into the air vertically upwards, its weight is acting downward. Due to this weight acting downward, while the particle is moving upward, this particle will get a retardation. You know the retardation is g. Like that, once the particle tries to move rightward, since this external force acting on the particle P is leftward, the particle P moves to the right with the retardation. And the other thing is, since this force F is increasing as the particle goes away from the point O. Why? The force F is given by kx. K is a constant, but x increases as the particle P moves away from O. X increases. The force acting on the particle P is given by F equals kx. Then you can see as x increases, F increases. Then once the particle P moves away from the point O, x increasing, then the force acting on the particle P towards the fixed point O also increasing. Then you can very clearly see here, people, according to F equals ma, F increases mean since m is constant, a increases. Acceleration increases. But this time this force is acting in the opposite direction of motion of the particle. What happens is, people, once the particle P is moving to rightward, its retardation is increasing. Retardation is increasing. You know what is meant by retardation? Retardation means the drop of the velocity in 1 second. So that drop of the velocity in 1 second, or the decrease of the velocity in 1 second, gradually increasing. That says in the first second, if the velocity dropped by 2 units, second it drops by 4 units. During the third second, it drops by 6 units. That is the meaning of retardation increasing. Then you can see, people, once the particle P moves away from the point O, its velocity is decreasing with increasing rate. Velocity is decreasing with increasing rate. What is meant by that? Velocity is always decreasing because of the retardation. That you can accept. But we said what? Once the particle is going away from the point O, F is increasing in the other direction. Due to that, retardation increasing. Retardation increasing means in 1 second, the decrease of velocity. That increases. Correct, Nodin? Due to that, what happens, people? The velocity decreasing of the particle P, and one occasion, the velocity of the particle will be 0. Suppose that point is A. Then no longer this particle can move to rightward because it has no velocity. Right? Then what happens? Particle actually can't stay there, people, at rest. The reason? Even though the velocity to the right is 0, people, the said force F is still acting on the particle P. And not only that, this is the location of the particle P, which is at the maximum distance from O. Now, when the particle is here, X is maximum. When X is maximum, people, this is maximum. Then that force acting on the particle is maximum. So therefore, no longer the particle can rest there. Because of the maximum force acting on the particle begins to move what? In the direction, AO direction, towards O. Since here the force is maximum, when the force is maximum, people, acceleration is maximum. Then particle begins to move from A with maximum acceleration towards O. But as the particle, people, coming towards this O, this X, the distance from O to this particle, it is X decreases. X decreases mean, since K is a constant, F decreases. That means once the particle moves towards O, the particle is always having an acceleration this time. What is the reason, people? The particle moves to leftward, the force also acting to the same direction. You know, when the direction of motion and the external force both in the same direction, because of that force, the particle gets an acceleration. So therefore, once the particle moves from A to O, people, the particle will get an acceleration always. But another thing will happen. What? As the particle comes towards this point O, you can see the X, the distance from O to the point, the particle P, decreasing, people. That means X decreasing means F decreasing. F decreasing means the acceleration is decreasing. So therefore, particle, when it moves from A to O, people, throughout the motion from A to O, since the force is acting in the same direction of motion of the particle will get an acceleration. That's true. But people, as the particle comes towards the point O, right? The acceleration of the particle gradually decreasing because of this force F act on the particle decreases. Okay, acceleration decreasing doesn't mean velocity is decreasing. You know, acceleration means what? In 1 second, increase of velocity. During unit time, increase of velocity is the acceleration. Then every instant, while the particle is coming from A to O, people, the acceleration, particle has an acceleration. Due to that, the velocity of the particle will increase. Only thing is, acceleration decreasing mean, people, in a unit time interval, the newly added velocity to the previous velocity of the particle gradually decreasing. That in the sense, early stage, the velocity increased by, say, 10 units in 1 second. Then the second people, the velocity newly adding to previous velocity is 9. Then now the velocity is 19. Third second, another 8 will add. 19 plus 8. Okay, 27. Like that, with the time elapsing, people, the newly adding amount of velocity, people, gradually decreasing. That's the meaning of acceleration decreasing. Due to that, people, since the particle has an acceleration, always throughout the motion from A to O, particle will increase its velocity, and therefore finally once the particle reaches the point O, since the particle had an acceleration from A to O, until the particle reaches to the point O, people, the velocity of the particle increases, and therefore particle will have maximum velocity when it comes to the point O. Due to that maximum velocity, people, particle will pass the point to the left. Once the particle passes the point O and coming to the left of O, people, suddenly that Z force is getting in the opposite direction. That gets opposite. Why? We said, people, always the external force capital F acting on the particle is pointing towards the fixed point O. Then what happens? Though the particle begins, that means passes the point O to move in the left hand side with greatest velocity at O, once it passes the point O to left, people, since this force is getting opposite, again the particle will be moving to the left of the point O. How, people? Decreasing its velocity. Why? Particle is moving leftward, but force is acting rightward. That motion is very similar to the motion of the particle when it was moving from O to E. The same motion the particle will experience. Due to that, with the increase in retardation, particle will be decreasing its velocity, and one occasion the velocity of the particle will be 0. Right, people? Will be 0. Suppose that point is A dash. At the point A dash, suppose the velocity of the particle is 0 toward this direction. Okay. Now, though the velocity of the particle is 0 to the leftward, people, particle cannot rest there. The reason why, people? The external force acting on the particle pointing towards this O is now maximum, because the distance from fixed point to the particle is now maximum possible. So therefore, no longer the particle will be resting there. Okay. Particle will begin to move in the opposite direction towards O with maximum acceleration. Why, people? F is maximum at this instant. When F is maximum, A is maximum. With maximum acceleration, particle begins to move from A dash towards O. Now this time, during the motion from A dash to O, people, the direction of motion of the particle and the force F both act to the same direction. So therefore, the particle will have an acceleration until it comes to the point O. But as the particle comes towards O, the F decreases because the distance between particle P and the point O decreasing as it comes towards the point O. X decreasing means F decreasing. F decreasing means people acceleration decreasing. So therefore, particle will experience the same motion it had while it is moving from A to O. The same motion now it experiences when it comes from A dash to O. But people from A dash to O, throughout that journey, the particle has what? An acceleration. Due to that, always until it comes to the point O, people, its velocity increases. So therefore, at the point O, its velocity becomes maximum. Due to that maximum velocity, particle tries to what, people? Pass. That passes really the point O to the right. Then what happens? That said force capital F gets opposite pointing towards O. Then again the particle will be experiencing what? The same motion, O A motion it had earlier. This way, people, the particle moves between A and A dash. Then this kind of motion is simply defined as, people, simple harmonic motion. Simple harmonic motion. Understand? So therefore, the main source which of course create this kind of motion for the particle is the variable force F. The force F varies such that its size is kx. Its size is, magnitude is proportional to distance from a fixed point to the particle. Because of that only, the motion creates. So therefore, this kind of motion only we define as simple harmonic motion. This fixed point, people, we define as the center of the simple harmonic motion. Center of the simple harmonic motion. And the maximum distance particle goes away from the center is called as, people, the amplitude. Amplitude. That means here, people, to the right from the point O, the maximum distance the particle can move is this. Suppose that is A, then A is the amplitude. And the other thing is, people, on either side of the point O, the behavior of the force F are like same, identical. So therefore, when the particle moves on either side of the point O, people, the motion of the particle P on either side of the point O, the motion of the particle P on either side of the point O, people, symmetric. Symmetric means when the particle goes away from the point O, when it is at a particular distance, suppose L, this particle will have to the right hand side direction particular velocity and particular retardation. And when the particle passes the point O to the left hand, when it is at the same distance L away from the O, while coming to leftward towards A dash, the particle will have the same retardation, right, and same velocity. Okay, and when the particle going away from O towards A, when it is at a distance simple L, the time taken by the particle to move from O to that distance L away from O is, people, same as when the particle is passing point O to the left, and when it is at a distance simple L from O, the time taken. That is the meaning of symmetric. This symmetric nature we have to expect, people. Why? The behavior of the force if alike on either side of the point O, identical. So therefore, due to these, people, what happens is the maximum distance this particle moves away from this point O to the left also the same way. That should be so. So therefore, then this particle is moving on either side of the point O the same distance. Therefore, you can say the amplitude being equal on either side of the point O. Right. And the other thing is, people, in this case, the plane is smooth. And while the particle is moving, no air resistance. So therefore, due to any reason, there is no loss of energy of the particle. There is no loss of energy of the particle. Throughout the motion, the initial energy the particle had. What is the people initial energy the particle had? Initially, the particle is projected from the point O with velocity u, no? Then the particle had kinetic energy. It is half mu square. People, this is the energy the particle has. Okay. Then you can see here, once the particle reaches here, its velocity is 0. Then what happened to that initial energy, half mu square, the particle had? People, that energy, initial kinetic energy, people, the particle used to do a work to move against the force F. Okay. Now this force F, you know, people, when we consider like this, suppose this way, a rough plane we have. We project the particle with initial velocity u. Because this is rough, once the particle is trying to move rightward, the frictional force acting leftward. People, one occasion, because of the retardation of the particle. Why does it get retardation? Because of frictional force act leftward. Now, you know, one occasion the particle will come to rest. Okay. Because of the kinetic energy the particle initially had. This amount of the energy particle initially had. Now particle wants to move rightward, but the frictional acting leftward, frictional force acting leftward. So therefore, to do work against the frictional force, the particle has to spend particular energy. Therefore, the particle little by little spend its energy from initial kinetic energy to do work against the frictional force. Due to that, its energy gradually decreasing and one occasion gets 0. No longer it has energy, therefore the particle will come to rest. Not like there are people in this case. In this case, a particular source creating this, what people? Variable force. Now, though this particle is moving to rightward, it has to do particular work to move against this force F. How? Doing particular work. To do particular work, people, the particle must have energy. What the energy it has is kinetic energy. It spends the kinetic energy to do work against what? This force F. But the source, this F force creates, people, that energy spending by the particle storing in it. Storing in it. Here, people, that energy waste through heat energy. But here, this source which creates this variable force, that source stores what? That energy spending by the particle. Then once the particle comes to rest here, the whole energy particle initially had, half mu squared, will be stored in the source which creates this variable force. Then what happens? That source little by little gives that stored energy to the particle. Then due to that energy, the particle will be what people getting that energy once it comes back to the point O. People usually, to create this kind of variable force, we use extensible string. Extensible string. Just consider here, once we use a extensible string this way, you know you have done this in physics, right? Once this way, extensible string, rubber string say, elastic string say, okay? Once we stretch, once we give an extension to the elastic string, people, there will be a particular energy stored in that. The energy stored in that we define as what? Elastic potential energy. So in order to create this variable force, that kind of source string we use, then that kinetic energy, once the particle is moving to rightward, kinetic energy decreasing, and that decreased kinetic energy stored in the string as elastic potential energy. Once the kinetic energy of the particle comes zero, people, that overall energy stored in the source, that is the source in this case, what people? The elastic string. Then that releases the stored energy again to the particle. So therefore, no change of what energy, there we assume no air resistance, no friction here, and not only that, people, inside elastic string also, you know, the molecule and everything, you know, small what particle available. Once the string is stretched, people, the molecules or the particles what collide each other. Due to that, you can very clearly experience when you stretch 2-3 times elastic string, this gets heat because of what? That friction inside that. That also we ignore. So therefore, people, no chance of what? Dissipating energy. So therefore, the particle has no any loss of energy. So therefore, converting this way, kinetic energy to elastic potential energy, then elastic potential energy to kinetic energy, this way, every day, forever, the particle moves on this motion. So therefore, theoretically, people, if we assume like that, this motion never ends. Practically, it is different from the situation because we can't find out the situation, there is no loss of energy. But theoretically, if we assume like that, there is no loss of energy, people, forever this particle is moving here and there, right, about the point O. So therefore, this kind of motion is people defined as simple harmonic motion, right? And the other thing is this. You can very clearly notice, once the particle moves between this A and A dash, you know, the particle has no constant acceleration or constant retardation. Particle has no constant acceleration, no constant retardation. The acceleration varies, retardation varies. So therefore, people, for the motion of this particle, in other words, for the simple harmonic motion, people, you can't apply that equation of motion we used. What are the equation of motion we use, people? V equals U plus AT. V squared equals U squared plus 2AS. S equals UT plus half AT squared. We can't use them because these equations of motion possible to use, people, when this acceleration is constant. When this acceleration is constant, you can see nowhere during the motion of this particle acceleration is constant. So therefore, you can't use what? Equation of motion. So there are separate set of equation of motion which are identical, typical for the motion, simple harmonic motion. That equation of motion today be obtained. They only we can use for the calculations to find out unknown regarding this simple harmonic motion. Okay, right. So this is the people, just the summary. So then furthermore, you can very clearly understand when the particle reaches to the center, its velocity is maximum. When the particle reaches to the center, the force acting on the particle is 0. according to F equals kx, when the particle is at the point O, x is 0 now. Therefore, at the center, particle has what people? Maximum velocity. Particle is acted 0 force. When the particle is at this corner, the position corresponding to the amplitude, velocity 0, but force acting on it is maximum. Okay. And due to the force is maximum, the acceleration acting on the particle is maximum when the particle is at instantaneous rest. Instantaneous rest means it is resting for 0 seconds time. Okay, they are the important properties you have to get by this motion. Right, people? Okay. Now, next thing is to identify the simple harmonic motion. Simple harmonic motion. You know, people, now in this case, if you have this ut0, then the equation coming as s equals half ATU squared if this u is 0. If u is 0, you know, initial velocity is 0 now. Then the displacement is given by half ATU squared. Then whenever you see this kind of equation, you can easily say this is an equation of a particle started from 0 velocity. Okay. Like that, by looking at the equation, we can get an idea about the motion. Like that, when any particle is moving in this way under simple harmonic motion, there's a characteristic equation, typical equation. For that motion, only this equation is valid. For any other motion, this equation is not valid. That is typical for that motion. That equation is called as the characteristic equation of the simple harmonic motion. That equation we can very easily obtain like this. You can very clearly understand, after projecting the particle from O at t equals 0, suppose after a time t, particle is at a point somewhere here, moving a distance, simple x. Then you know people, at time t, the acceleration of the particle is marked as x double dot, the velocity is marked as x dot. Then I can apply for this motion of the particle F equals ma. There F force is given by kx. Then when I apply for the particle, this F equals ma rightward, the force is acting leftward F, mass is m, acceleration is rightward x double dot this way. Right, people? So then this force really, not F really, it is minus F, because F equals ma, we apply rightward, force is acting leftward, acceleration is rightward. Okay, then this force is minus F. Substitute for this F here, kx, then this way we get. Then taking this here, we can subject this x double dot. Therefore, x double dot is equal to minus k upon mx. This k upon m we take as omega squared. K, we said the positive constant, m is positive. So therefore, k upon m is positive. Then you can write that as a perfect square. Right? So therefore, omega squared equals k upon m now. Then I can write omega squared here. Therefore, we get x double dot is equal to minus omega squared x. X double dot is the acceleration. X is a displacement. Then between the acceleration and the displacement, we have this kind of relationship. This kind of relationship. Acceleration is equal to minus omega squared x. X is the displacement from the fixed point O, from the center. So this is called as the characteristic equation of the simple harmonic motion. So therefore, when you are given a particle performs a motion subject to the equation this, x double dot, the acceleration is equal to minus omega squared times x. People, that particle is definitely moving under simple harmonic motion. Why? This kind of equation belongs only for what? The simple harmonic motions. It is therefore said as what? The characteristic equation of the simple harmonic motion. Its right hand side, people, after this minus sign and the constant, what do you have? X. Once you bring this x 0, this gives us what, people? The position of the center. We know we define the center as how, people? At the center only, the force acting on the particle is 0. Okay. If this force is 0, acceleration is 0, people, according to F equals ma. Acceleration is x double dot. If this x double dot is 0, since this omega squared is not 0, x should be 0. So therefore, if we have the characteristic equation of simple harmonic motion, using that, you can very easily find the center of that motion. What you need to do is, people, on the right hand side, after the constant figure, what do you have here? Sometimes in this place, there can be a linear expression in x. Whichever it is, people, we equate that to 0. Then we get x value. Then according to that x value, you can find out the corresponding point. That point is the, people, the center. The center, right? So then, of course, we can identify the center, the position of the center, by observing the characteristic equation of the simple harmonic motion. Okay, right. The next thing is, we said, people, that the equation of motion we can't use to find any unknown relating to this simple harmonic motion. Then what are the equations? Let's see what are these equations, right? So then the first one, okay, what is that? X double dot is equal to minus omega squared x minus omega squared x. This is the characteristic equation, right? Let's see. This is now one equation, people, relating the acceleration and the displacement. Okay. The next one is the relation between velocity and the displacement. Now, this is the relation between acceleration and the displacement. The second one, we are going to obtain relation between velocity and displacement. That can easily be obtained, people, like this. You can very clearly understand this x double dot is the acceleration. No, you can write that as dx dot divided by dt. This way you can write minus omega squared x. Dx dot divided by dt means what, people? First derivative of x dot, first derivative of the velocity. First derivative of the velocity with respect to time t is the acceleration. This one coming. Then I write this this way, people. Dx dot divided by dx multiplied by dx by dt, like this. We write it like this. Then you can see by chain rule in the differentiation, this dx and this you can cancel down. Dx dot divided by dt coming. It is, people, what? Omega squared dx on the right hand side. But you know what is this dx upon dt? This is nothing but x dot, no? This is x dot. Then we get here, people, this dx dot divided by dx times x dot. This is x dot now, equals minus omega squared dx. We bring this dx to what, people, right hand side. So then we get x dot times dx dot equals minus omega squared x dx. Okay, people. Now what we do is this. We integrate both sides. Left hand side with respect to x dot, right hand side with respect to x. Then once integrate, what we get is this x dot dx dot equals minus omega squared is a constant. You can take that out from the integral sign, x dx, like this. Well, you know, the integral of x dot with respect to x dot going to be what? X dot squared by 2. x dot squared by 2 equals minus omega squared integral of x with respect to x people x squared by 2 plus people c. C is a constant. C is a constant. In this case, c is not an arbitrary constant. This c has a particular value. So therefore, we write only c is a constant. Right? C is a fixed value. That means c is a specific constant. It has a definite value, people. Usually, you know, after every integration, we write that c has any arbitrary constant. That means any constant. In this case, c is not any constant. It is a constant. It is a constant. That constant has a specific value. So therefore, c is a constant. Now, how to find this c, people? How to find this c? C can be found like this. You know, people, this x is measured. The x is what, people? The distance from the center to the particle. Once the particle reaches the point capital A, this x will take simple A, the amplitude. When this x take this simple A, particle is here, then the particle has a velocity 0. That means you can write when x equals A, x dot, the velocity of the particle is 0. That's true, no, people? That means the particle, when the particle reaches the point A, x takes simple A, the velocity of the particle is 0. Then we can put them where here. 0 squared by 2, omega squared, x is, people, a squared by 2 plus c. Okay. Now you can bring this to this side. This is 0 now. C is omega squared a squared by 2. Then that is the, you know, people, this omega is a constant. A also a constant for this motion. So therefore, this c is a, people, a fixed value. That is not any constant. That constant has a fixed value. That is why I said that c is not an arbitrary constant. So now this c we can put there. Then we get what, people? X dot squared by 2 equals minus omega squared x squared by 2 plus c mean, people, omega squared x squared by 2. You can cancel down these two on both sides. Then we get x dot squared is equal to, bring that omega squared out from the right hand side. What do we get? A squared minus x squared. This is the, people, relation between the velocity x dot and the displacement. Right? Whenever we need to find something which relates velocity and the displacement, this is the, people, equation of motion we have to use for the simple harmonic motion. What is that? X dot squared is equal to omega squared. Omega squared is the constant which is available where? In the characteristic equation here. Then what is inside the bracket? First thing, A, amplitude perfect squared minus x squared. What is this x, people? X is the distance to the particle from the center of the motion. So that is that relationship between velocity and the displacement. Another one more. That is the relation between displacement and the time. That also, people, we can obtain by using this. That also we can obtain by using this. Right? What is that? We can obtain it like this. The relation between displacement and time, we can obtain like this. People, remember, though we have this kind of equations, once we work out questions, I think among all the applied lessons, you will feel this is the easiest one. Very interesting, very easy lesson. Right? You might sometimes say at the beginning of every lesson, you say like that, but we only know that. So on. But people, this is very easy lesson. 150 marks you can very easily pick. So therefore, this should be another one question that you need to do at the examination. Right? Very easily you can score marks by this. Very easy questions, very interesting. This is all the theories, people. And the next thing is we have to do some more sums in order to practice the pattern of the questions. Then very easily you can score. Now, of course, at the examination, very easy questions are coming. When we do like 15 16 questions in this lesson. People, I think this lesson will be very easy one. Then I think now you have done that center of gravity, no? How do you feel about the center of gravity, people? More work. But people, once you do more sums and practice doing more sums, I think very easily you can work out any question under this center of gravity. It's of course, there are more works in it. But compared to the center of gravity, people, the simple harmonic motion you will find very easy than that. But remember, we must do at least 15, 16 questions we must do. In center of gravity also, I think I did 17 questions. 20 questions. The discussion, I put the recording link to the group. I think everybody watched that, and watching that, complete the notes. Okay. Last Sunday we did that in the Kurunagal group, so that recording I put in your group. I think almost all watched that. Did you watch that, people? No. Watch that, and that is available. Right. Now the relation between the displacement and time t, right? We can obtain like this. X dot squared is equal to omega squared times a squared minus x squared. No, we can take the square root on the right hand side and subject x dot. Omega squared will be omega. This is the root. Now, people, this x dot mean it is dx by dt, no? Dx by dt, right? Omega this. We have this way, right? Now, here also we use the integration technique to get this answer. I bring this square root part to our left hand side denominator, this dt, right hand side numerator. Then we get 1 upon square root of a squared minus x squared dx equals omega times dt. Okay, now we can integrate both sides. Integrating both sides. What do you get there? 1 upon square root of a squared minus x squared dx. Omega is a constant, we can take that out. Then on the right hand side, we have to integrate 1 with respect to time t. Can somebody tell me what is the integral in the left hand side? Yes, it is, people, sin inverse x upon a. Sin inverse x upon a equals, here this is t, no? Omega t plus, people, a constant, I take this as k. Right? K is a constant. Okay. Now, once you bring this sin inverse to right hand side, we can write x upon a equals sin omega t plus k. Right? Now we can use the cross multiplication by this a. Then we get x equals a sin omega t plus k. Now that omega t and k should be angles, people. They should be angles, right? So this is omega t is an angle, right? Suppose this is a or alpha, say this k, suppose beta. Then we have within bracket, we have alpha plus beta. Then this is nothing but sin alpha plus beta, sin a plus b form it has. Sin a plus b. You know, sin a plus b, we can expand sin a cos b plus cos a sin b. So once you expand like that, people, you get something like this. X equals, right, a sin omega t cos k plus cos omega t sin k. Sin a cos b plus cos a sin b. Now we take this cos k. K is a constant, people. Then cos k is a constant. This a also a constant. This a also a constant. Then cos k is a constant. This a also a constant. This a also a constant. Right. Okay. Then here, a and this cos k we can multiply, people. A cos k sin omega t, and this a and sin k, a sin k times cos omega t. You know, k is a constant, then cos k is a constant. A is a constant. Why? A is the amplitude, people. Amplitude is a constant. Therefore, a cos k is a constant. Then this a cos k I will take as, people, capital A. Similarly, this a sin k also a constant. We will take that as capital B. Then we get x equals a sin omega t plus b cos omega t, where a, b are constants. So therefore, this is the relationship between, people, displacement and the time t. Displacement and time t. So therefore, what are the three equations? Now in this case we have, people, x double dot t is equal to minus omega squared x, the characteristic equation. Second one, x dot squared is equal to omega squared times a squared minus x squared. Third one, this x equals a sin omega t plus b cos omega t. They are the three equations we can apply to find any unknown related to the simple harmonic motion. That equation of motion, people, we can't use in this case. Okay, right. So this is the summary. And people, another one more theory part available. Right? That theory part we'll discuss, getting a note by this. Thereafter, I think we can start the today paper question, the questions in the lesson. Right? Any question here, people? Any question you have here? Right. We'll do the diagram here. Over here, particle is here P at a distance x at time t equals t. Right. So then this is a fixed point. Fixed point. Right. This velocity is x dot. Acceleration is x double dot. Particle reaches to point A. Velocity 0. Right. And descend the same distance. By t dash. Right, this is 0. Suppose this distance is A, the amplitude is also A. Right. At first draw this diagram. Draw the diagram first. Right, people, now we'll write down a brief note regarding this, and then we'll try to finish today all the theories and come to the questions. Right now. Okay, now write down like this, people. Write down, suppose a particle P of mass m, suppose a particle P of mass m moves on a smooth horizontal plane. Let O be a fixed point on this plane, a fixed point on this plane. Now write down, suppose a force capital F acts on the particle P which is always pointing towards the fixed point O which is given by capital F equals kx, capital F equals kx, where k is a positive constant and simple x is the distance, from the fixed point O to the particle P. Right, start from new line, people. Now suppose the particle P is projected with a certain velocity from the point O on the plane. Write down in the subsequent motion, in the subsequent motion, in the subsequent motion. In the subsequent motion. Subsequent motion means people in between motion. That means the motion occurring next. The motion occurring next is a subsequent motion. In the subsequent motion, particle P experiences the following. Write down people number 1. Write down number 1. Write down as the particle moves away from O, the force capital F acts in the opposite direction of motion, acts in the opposite direction of motion of the particle and therefore particle gets a retardation. But since the force capital F increases, as the particle P moves away from O, the retardation of the particle P increases and at a moment its velocity becomes zero. And suppose the particle is at the point capital A. Suppose people write down, suppose at this moment particle is at the point capital A. Suppose at this moment. Right. Now write down people number 2. Number 2, write down second point. When the particle is at capital A, when the particle is at capital A, the force acting on it, the force acting on it, the force acting on it is maximum, and therefore particle begins to move from A towards O, from A towards O with maximum acceleration, with maximum acceleration. But as the particle moves towards O, since capital F decreases, since capital F decreases, due to the decrease of simple x, due to the decrease of simple x, the acceleration of the particle decreases and it becomes zero, it becomes zero when the particle reaches point O. Reaches point O. During the motion of the particle, during the motion of the particle from capital A to O, since it had an acceleration throughout this motion, velocity of the particle increases and it is maximum at the point O. At the point O. Right, people, number 3, third point, write down. Number 3, third point. Now the particle passes the point O and begins to continue its motion on the left of the point O. Then suddenly the variable force capital F gets opposite pointing towards the fixed point O. Therefore, on the left of the point O, the particle experiences the same motion as it had from O to A motion. Write down paper. Same line, write down. Suppose particle comes to instant rest, or instantaneous rest. Suppose the particle comes to instant rest at the point capital A dash. Write down, people, the fourth point. Fourth one. Now particle begins to move from A dash towards O, experiencing the same motion it had from A to O. People now write down, start from new line. Write down. In the above manner, the particle continues its motion continues the motion. This motion of the particle is called as simple harmonic motion. Simple harmonic motion. And the fixed point O, is called as the center of the simple harmonic motion. The center of the simple harmonic motion. Right, start from new line, people. The motion of the particle is symmetric about the fixed point O. Therefore, the maximum distance the particle moves away from the point O on either side of O. Are equal. This maximum distance is called as the amplitude of the motion, of the simple harmonic motion. Write down. The velocity of the particle the velocity of the particle after moving a distance which is equal to amplitude from the center is 0. Is 0. Right, people. We'll come to the next part. Write down next subheading like this: characteristic equation of the motion. Characteristic equation of the simple harmonic motion. Right, no? Okay. Right. Now you can write. We have drawn this t equals t, no? Right. Now you can write at t equals t, applying for f is minus kx, right? If x leftward, no? F is given by kx. We wrote that, no? Mass is m, acceleration is x double dot. Then x double dot we can write minus k upon m times x. Let omega squared is k upon m. Then we can write x double dot is equal to minus omega squared x. Is called as the characteristic equation. Right. Write down. This equation is known as the, write down these people, this equation is known as the, characteristic equation of the simple harmonic motion. Right. People, how to obtain the center? After the constant, what do you have here? Sometimes here we can have an expression in x. That whole expression equal to 0 and find x. That corresponding position for that result in x is the people center. Or in other words, we know center is defined how, people? The point where zero force acting on the particle while it is moving in the simple harmonic motion. That point only is the center. And the other property at the center of a particle is, at the center, particle has the maximum velocity. Right? Remember this story, right? When you work out the questions, this story is very important. Right? Okay. Next one, people, we can write. Put a star mark like this. During the motion of the particle, during the simple harmonic motion of the particle, write down like that. During the simple harmonic motion of the particle, the acceleration of the particle is not constant. Therefore, the equations of motion cannot be applied to find any unknown relating to the simple harmonic motion. Right. Now we will write down next one, the relation between velocity and displacement. The relation between velocity and displacement. Velocity and displacement. Yeah. Retake that like this, people. X double dot is equal to minus omega squared dx. Then here we can write x double dot dx dot by dt is minus omega squared dx. This dx dot by dt I can write, people, like this: dx dot by dx multiplied by dx by dt minus omega squared dx. People, dx by dt is nothing but x dot. No, this is x dot. Right. X dot. Dx dot by dx minus omega squared dx. Now write this: x dot times dx dot, this 2, and bring this to right hand side, minus omega squared dx dx. Now integrating both sides. We write that like this: integrating both sides. Take this: x dot dx dot equals minus omega squared. We can take out because it's a constant, x dx. Now the left hand side: x dot squared by 2 equals minus omega squared x squared by 2 plus c. C is a constant. C is a constant. But you can write, but at x equals to A means here people the amplitude, is the amplitude. Write on that here. At x equals A, x dot is 0. Put that here. Right now, when the particle reaches here, x is A, velocity is 0. Put that here. 0 squared by 2 is equal to omega squared A squared by 2 plus C. This is 0 now. This implies C equals omega squared A squared by 2. Now you can put that where here. Put that for that place of C. Therefore, we get x dot squared upon 2 equals minus omega squared x squared by 2 plus C is omega squared A squared by 2. 2, 2, 2 you can cancel now. Right, what do you get there? Take omega squared out. This is the relation. Is the relation. This is the relation, right? Right, we'll write the meaning of this. A is the amplitude, x dot is the velocity, omega squared is the constant in the characteristic equation. X is the distance to the particle from the center. Remember, right? X is the distance to the particle from the center. This x, here this x has been measured from the center. Okay, right. And then we'll write the meaning of that. Write down, under that, write down x dot, the velocity. A is the amplitude. X is the distance to the particle from center. Omega squared. Constant in the characteristic equation. Characteristic equation. Right now. Right, people, now we'll write the next one. Write down the relation between distance and time. The next one, write down the relation between distance and time. The relation between distance and time. Distance and time. x dot squared is equal to omega squared times a squared minus x squared. Right. You can subject x dot by this omega, take root this. This x dot you can write, people, dx by dt, no? Right. Now, you can separate the variables dx divided by, I take this to this left hand side, denominate like this, dx equals omega dt into 18. We get like this. Equals omega times 1 dt. This is sine inverse x upon a. Equals omega t plus k, people. I take the constant as k, where k is a constant. Where k is a constant. Now people bring the sine inverse to right. We get x upon a sine omega t plus k. X equals a sine omega t plus k. Now I can remove the brackets. I read it here. X equals a times sine omega t into cos k. Cos omega t into sine k. Sine a cos b plus cos a sine b. A and this cos k, when you multiply, a cos k times sine omega t. A sine k times cos omega t. Be it, huh? You know, people, this a cos k is a constant. Say it is a. A sine k also constant. Say that is b. Therefore, x equals a sine omega t plus b cos omega t. Where a and b are constants. Right. Here also, people, this x is what? The distance from the center to the particle. Omega is the square root of the constant available in the characteristic equation. You know the characteristic equation we had like this, no? X double dot is equal to minus omega squared x. Right? The root of this only come in here, people. Right? This x only come in here. A and b are two constants. T is the time the particle moved in simple harmonic motion, right? So that is the relation between displacement and time t, right now. Okay. Right now, people see like this. The center is O. The distance measured from O to the particle P. Right? I'll come that through an example, right? When we do a question, right? Okay, now we'll come to the next one. Right, it is this. When we consider simple harmonic motion, people, for any simple harmonic motion, there is a corresponding circular motion. There's a corresponding circular motion. There's a corresponding circular motion. Right. We can very easily prove it like this. Right. I'll take people this way. Try the next heading like this. The relation between simple harmonic motion and the circular motion. Right, people. Suppose like this, on a circle, a point P moves with constant angular velocity omega. Suppose this is the circle, right? Assume this as a circle, right? Right, no, this time we have to assume this as a circle. Like this, right? Okay, people. Right, now suppose here, this is a circle of center O, and suppose radius E. I draw the two axes X and Y like this. Y-axis and X-axis. This is O. People, center is O, radius is A. This is negative X-axis. This is negative Y-axis. Right. Now suppose a point P moves on this circle with constant angular velocity omega. This is a P. Point P. Point P moves on the circle with constant angular velocity omega. Suppose at this moment, the point P lies on the circle with the coordinates x, y. So then from this point P, I drop a perpendicular to the x-axis like this. I'll take this perpendicular foot as people Q. Right. Suppose this is the time t after starting the motion of the point P. Right. This is the perpendicular foot. Here, this is 90. Right. So the distance from O to this Q is X. At time T, right? Now, when I join this O and P people, this OP, I am going to take, makes an angle theta with the positive x-axis in anticlockwise. This way. I take like this. Okay, right. Then we'll write one sentence like this. Consider a point P. Consider a point P which moves on a circle, which moves on a circle which moves on a circle with center O and radius A, with center O and radius A, with constant angular velocity omega, with constant angular velocity omega. We will draw this diagram first. Draw this diagram first. This is 99. Draw this diagram first. Right now. Right, people will write one sentence. Now write down like this. Suppose at time, t equals t, the point P is at the point within bracket x comma y on the circle. Write down. Let the perpendicular foot drawn from drawn from P on x-axis. Then the perpendicular foot drawn from P on x-axis, B, capital Q. Right. Well, now you can see when this way a particle P moves on a circle with constant angular velocity, you know, centripetal acceleration. You know, the centripetal acceleration is, people, A omega squared is the centripetal acceleration, A omega squared. The radius is A. Omega is the angular velocity of the particle that moves on the circle. We know this, right? Now the study the behavior like this. Suppose the particle P starting its motion from this point where the circle and the x-axis intersect each other. Then you can see once you bring this particle P back to the point Q, as the particle P comes along the circle like this, people, the point Q also coming towards this way. Why? Point Q is the perpendicular foot drawn from P on the x-axis. Then P, when P is here, Q is here. You can see that very clearly. P is here, Q is here. Like that, once P comes along the circle to the point, this Q coming toward this point. And finally, when the point P is here, Q also there. Right. That's a very obvious thing, no? Yeah. Now suppose, people, the point P moves from the circle and comes to here. Then you can see point P has two motions. Point P has two displacements. One is initial the point P, now here, that has moved horizontal displacement A. Meantime, that has gone up the vertical displacement A. That is why we say the particle P, not the particle P, point P, which moves on the circle, has two displacements, two motions, horizontal motion and vertical motion. Okay. Yeah. Now particle P comes from here to here. Then its horizontal displacement is, people, simple A. And that occasion you can see the point Q also coming from here to here. Why? When the point P is here, once you drop a perpendicular from there on the x-axis, point Q comes to this. That means when the point P comes on the circle from here to here, right, the point Q comes to the point O. You can see during the same time interval, both the particle point P and the point Q moves horizontally the same displacement A. Next thing, when the point P moves from here on the circle up to this point, what happens to the point Q? The perpendicular foot of P on x-axis, Q will be coming from here to here. Again, see the point P on the circle that has moved horizontal displacement A. During the same time interval, people, the point Q also move in the same horizontal displacement. People, you can see a particular relation between the motion of the point P and point Q. What is that? The horizontal motion of point P and point Q being equal, being the same, identical. That means during the same time intervals, the horizontal displacements of the point Q and point P that moves on the circle being same, people. Right? Horizontal displacements, horizontal motion only we consider in this case of the point P and point Q. They are the same. During the same time interval, the horizontal displacement of P and Q being equal. Right? People, for this to occur in this way, during the same time interval, displacement should be people. This displacements being equal. No? For this way to occur the motions, definitely at any moment, the horizontal velocity and horizontal acceleration of the point P should be equal to what? The horizontal velocity and horizontal acceleration of the point Q. Otherwise, this situation we can't observe. Is it clear? When you consider the horizontal motion of point P and point Q being the same. So therefore, at any moment of the motion, people, the horizontal velocity of point P and point Q must be equal. The horizontal acceleration must also be equal of them. Otherwise, we can't see this kind of motion. So therefore, even at time t equals t, the horizontal acceleration of the point P, horizontal acceleration means parallel to x-axis, right? The acceleration should be equal to acceleration of Q, right? You know, people, at time t, the horizontal acceleration mean the acceleration component of this point P parallel to x-axis this way. If this is theta, this is also theta. Then this way the acceleration component is a omega squared cos theta. And at time t equals t, the horizontal acceleration of point Q is people x double dot. X double dot. Why? At time t, the point Q is at a distance simple x from O. Right? I'll take this point as A, this point as A dash. Then at time t, you can equate what? The horizontal accelerations of P and Q. What do you get? At time t equals t, right? Acceleration of P should be equal to acceleration of Q. Okay. Acceleration of Q, rightward direction x double dot, right? It is the rightward direction. Okay. Here also, when you put the rightward direction, a omega squared cos theta is people acting leftward. So therefore, that must be minus a omega squared cos theta. This one you can write as minus omega squared a cos theta. X double dot. People, what is a cos theta? What is a cos theta? The distance, this, the radius is your a. This is theta. So therefore, people, a cos theta means this x. But you can write, but a cos theta is equal to x. Then I can put for this a cos theta that x. And therefore, x double dot is equal to minus omega squared a cos theta. A cos theta is x. All right. What is the result, people? What is the result? The motion x double dot is the acceleration of the point Q. Then the point Q has the characteristic equation of the simple harmonic motion. That means the point Q moves on simple harmonic motion. Its center x equals 0 means this point. The point Q moves between A and A dash. The point Q can't move beyond this A dash leftward and beyond away that A. So therefore, point Q moves between A and A dash. center is O. Since the radius of the circle is simply the amplitude of the simple harmonic motion is simple A. So therefore, while the particle, the point P moves on the circle with constant angular velocity omega, the point Q moves in a simple harmonic motion as the center O and radius simple A as the amplitude. Right? People, the most important thing is the other way around. But here we started the story by the circular motion of the point P. The other way around. People, if we set the particle Q to move on the x-axis subject to this condition, correspondingly, you can see, people, the particle P moves on the circle with constant angular velocity, this figure omega. This says, people, for any simple harmonic motion, there is a corresponding circular motion. Of the circular motion, the center of the circle going to be center of the simple harmonic motion. Radius of the circle going to be amplitude of the simple harmonic motion. The constant angular velocity of the particle that moves on the circle, constant angular velocity going to be this figure. Right, people? That way we can, right? We can get corresponding circular motion for any simple harmonic motion. People, this one is very useful to find the time the particle that moves on the simple harmonic motion to complete particular journey. That occasion, we consider the corresponding circular motion and we consider the 2 points that particle that moves on the circular motion during that motion. Then using that, of course, we can find the time the particle that moves in simple harmonic motion taken. Okay, right now. Then what the people think we wrote? Can someone tell me the place we finally stopped? Yes. Right. Okay. Now we can write like this. Okay. Now write down like this. As the point P moves on the circle, as the point P moves on the circle, it has two motions. It has two motions parallel to the axis capital X and capital Y. Parallel to the axis capital X and capital Y. The motion of P, parallel to x-axis is completely described by the point Q. The point Q. Therefore, the velocities and accelerations Therefore, the velocities and accelerations of P and Q at any moment parallel to x-axis, should be equal. Write down. Equating the accelerations of P and Q parallel to x-axis at time t equals t. People, you have to mark all this, everything, right? This everything you have to mark, because this proof was came in 2006 paper, I think, 2006 paper to prove this. So therefore, it's important, right? Mark everything and take down this. Then obtain this. Right. Okay, now can write like this. Write down. After reaching here, now you can write, right? This implies the point Q moves in simple harmonic motion. The point Q moves in simple harmonic motion with center O and radius, with center O and the amplitude A. Write down. Then the converse result is as the point Q moves in simple harmonic motion with center O and amplitude A with center O and amplitude A, the point P moves on a circle with the same center O and radius as the amplitude of the circle. Radius as the amplitude of the simple harmonic motion. Radius as the amplitude of the simple harmonic motion. Right. Right. People, like this, for any simple harmonic motion, we can find corresponding circular motion. Right. Now, let's see the next one. Okay. Now, people, using this, we can find the period of simple harmonic motion. Period of simple harmonic motion. People, period mean now the point Q moves on a simple harmonic motion, no? Like this. Okay, now suppose that point Q begins its SHM from A, starting from A, passing through O, coming to A dash, and comes back to this A through this O. Starting from A, going to A dash, coming back to A. People, that motion is defined as one oscillation. One oscillation of the simple harmonic motion. One oscillation. The time takes to complete this oscillation is called as, people, the period of the simple harmonic motion. Now, period of the simple harmonic motion can easily be found like this. Now, people, you know, when the particle Q starting from A, coming to A dash and coming back to A, during that time interval, that point P with constant angular velocity omega, people, starting from A, completes the whole circle. Okay. When Q begins here, P also begins. That begins from here. When Q comes to this O, P comes on the circle toward this point. When Q comes to A dash, during the same time, P comes to the point A dash. Then when Q comes to O, on the circle, P comes to this point. When Q comes to A, P comes to A on the circle. Then the time taken by Q to complete that journey is equal to that of P taken to complete one circle. Therefore, the period of the simple harmonic motion is equal to the time taken by the particle P to complete one journey. You know, the particle P turns about the point O through an angle 2 pi during its motion. That 2 pi angle, it turns with the constant angular velocity omega. Then the time taken is, people, the angle divided by angular velocity. Therefore, period of period of simple harmonic motion is 2 pi by omega. T equals 2 pi by omega. T equals 2 pi by omega. Right, people? T equals 2 pi by omega. Right. Now write down like this. Write down the time taken by the point Q the time taken by the point Q to complete a single oscillation is called as its period, is called as the period of SHM, simple harmonic motion. Write down within record. Single oscillation is moving from capital A to A dash and back to capital A on the x-axis, and back to capital A on the x-axis. Close bracket. Write down during the time point Q completes an oscillation the point Q completes one circle or one revolution, one circle. Therefore, the time taken by point P is, therefore, the time taken by the point P is T equals 2 pi by omega. T equals 2 pi by omega. So therefore, the period of simple harmonic motion is T equals 2 pi by omega. T equals 2 pi by omega. Right now, people, this is all the theories. This is all the theories. Okay. Now we can start the question discussion. You want a break? Right, people. Right. Then take people in the evening. I put you a tutorial. It's a question number 20. Right. Take question number 20 in the tutorial. Right. Yeah. Okay, people, now these questions, remember, very easy questions, but more works available at the beginning, right? Right, till the end of the question, people, it takes nearly 1 hour to discuss the question. I can discuss this within 10 minutes, right? So then that is useless. But anyway, people, we take more time and then we'll completely discuss this situation and then get the idea. This lesson and the working out questions in the lesson is, people, very easy, right? So now till we do 4 or 5 questions, people don't go to work out bigger questions, touch the same questions, and thereafter I'll tell you the time that occasion you have to try the questions. Okay, right. Now take question number 20. It says something like this. One end of an elastic string of natural length A and modulus of elasticity mg is fixed at a point O on a smooth horizontal table. Point O is at a distance 2A apart from the edge of the table. The other end of the string is attached to a point P of mass simple m. One end of another light in elastic string carrying a particle q of mass simple m passing over the edge of the table perpendicular to it is attached to a particle P. It's attached to a particle P. Right. Okay. The particle P is released from a point at a distance simple a from O. Show that the length x of the elastic string satisfies the equation this. If the solution of the above equation is given by this AB, find the constants AB, hence so that the particle P reaches to the edge after time this much with velocity this. Right. It's a good question. People read the question again, try to understand the question again. Otherwise, if you don't get this picture into your mind, people, brain, though I work out this question myself, you won't get this any idea. Right. First, we have to have the figure in the question, right? The question is this. Number 20. By this way, we have a table. On the table, there is a point O. The distance from this O to the edge of the table is 2A. Right? Okay, and given elastic string of natural length A and modulus of elasticity mg. Elastic string means, people, you know, elastic means, you know, elastic means stretchable one, no? Elastic string. Take a rubber string. Rubber string you can, of course, imagine, no? Yeah. Such string, people, now when we consider such elastic string, right? Such elastic string, when the string is not given a force, right? When the string is not given a force, suppose we keep this string in straight without giving a force, then we keep the string in straight without giving a force, then its length is called as the natural length. The natural length is given as simple A. Right. People, now to this string, when we give another extra length by pulling this away, this way, this extra length is called as the extension. You know this. In physics, we have done. When this way an extension come into this string, in the string, people, a tension will be created. In the string, a tension will be created. Right? That tension is given by, people, T, suppose lambda x upon L. Lambda is called as the modulus of elasticity. X is the extension. L is the natural length. Okay, you can very clearly understand, people, when we consider such elastic string, when we increase the extension, right, people, you can see more force acting on our hand, right? That means as extension increases, tension increases. The tension is given by this formula. Lambda is called as a modulus of elasticity. Okay, right. So this one you have learned in physics, no? Under elasticity. Huh? No? Yeah. That is learned in another way, in the sense another name. Lambda is in this case modulus of elasticity. Right. X is extension. Right. So then if you need, you can mark this. Right. Such string is people joined. Right. To the point O. Right. Like this. And other end of that elastic string is people joined to the point. One end is joined to the point O. The other end, people join to the particle P, like this. Particle P of mass M. This is elastic string, huh? Mass is M, right? Okay. This length is A. This length is A. Right. Now, another inelastic string. Right. Inelastic string carrying a particle Q of mass simple M passes over the edge of the table perpendicular to it, is attached to the particle P. Right. Another string, people, that is inelastic. Inelastic means inextensible. We can't stretch that. So far in our lessons in applied maths, we have used inelastic strings, people. Inelastic, that means inextensible. Extensible means stretchable. That means rubber string like. Inextensible mean, people, we can't stretch that. So such string is the second string, right, like this. That passes over the edge of the table. Its one end is joined to the particle P. Other end, people, carrying a particle Q of same mass. This is Q. Same mass, right? Now, what's the question given next? The particle P is released from a point at a distance simple A from O. All right. Show that the length X of the elastic string satisfies this equation. People see the way the question given. This is the honest thing given. People, now after getting this information, now you have to first understand what is really happening there. That's why I told you, until you do 4 or 5 questions, people, the behavior of the question you can't understand. You have to do some questions. Till then, don't be hurried. Okay, right? Okay, now this is what really people happens there. This Q has weight mg, no? Because of the weight mg, this particle moves downward. Then the tension T creates in the inextensible string. That tension throughout the string being equal, people, of this. This is inextensible, not stretchable. This is the elastic, extensible, right? Okay, that tension acts on the particle P. Thereafter, because of that tension, the particle P tries to move this direction. You know this elastic string at the moment in the natural length A. Once the particle P tries to move leftward, the elastic string will get an extension. Once it gets extension, people, subject to this equation, the tension T creates in the elastic string acting to the rightward. Now P is trying to move what, people? Leftward. That tension in the elastic string now acting rightward. Not only that, as P moves to the left, the extension of the elastic string increases. As the extension of the elastic string increases, people, as this x increases, the tension increases. See what happens? The particle P tries to move is leftward. Once the particle P is moving leftward, the right force, right tension on the string acting on the particle P is increasing. Particle P trying to move this way, it is moving leftward. That tension T in the elastic string increasing. People, that situation you can now compare with what? The simple harmonic motion definition. See here, the particle here P trying to move this way, then the force F increasing, point in the other direction. People, that is the force, that kind of force only people need to make a simple harmonic motion. See here, in the very first illustration in the lesson today, we discussed particle P trying to move rightward. The force F is acting leftward. As the particle P tries to move rightward, the force F acting leftward is increasing. Such force only people need to create simple harmonic motion. That kind of force is acting on the particle P. Then people, the particle P will undergo simple harmonic motion because of that variable tension acting in the elastic string in the left hand side. And that one you have to first understand. So therefore, in that way now, simple harmonic motion really occurring for the particle P. That we have to first understand. Next thing is this, people. Whatever the question, the given information in the question, people, is regarding just before starting the motion. Just before starting the motion, instant only, people, in the question you are given. Okay, right. So now here also the same way, you know, just before starting the motion, you are given. What is the thing given? P is released, keeping at a distance simple a from O. With this string taut. Yeah. Then people, you have to first identify what will happen after that. Thereafter, people, whatever your question given, allow this system to move a small time interval simple t. Allow the system to move during a small time interval t. And after elapsing the time t, people, draw the new diagram. Understand? What is the usual method? This is a rule, people. Rule means sense, I see this as a rule. If you practice like this, people, no chance of going wrong, people, when you do after 2-3 questions. Allow the system to move a time interval simple t, small time interval. Then what happens? We take, this is the initial instant, no, that we take as t equals 0. Because t equals 0 means soon after this instant, soon after releasing the particle P, people, the particle P enters into the simple harmonic motion. But some questions are there, people, soon after releasing the system or the particle does not begin the simple harmonic motion. We discussed that question the second time, as our second question. That also we have to distinguish very carefully, understand. Okay, in this case, soon after releasing the particle P, the right string exerts a variable tension such that as P moves leftward, tension increase in the other direction. That occurs soon after releasing the particle P. Then we say soon after releasing the system, the particle B begins the simple harmonic motion or enters into simple harmonic motion. That also we have to very carefully understand, right, by observing the question. Okay, right. Now we allow this system to move a time interval simple t, and that diagram we must draw secondly, right? So then I am going to draw that now. Right, so then t equals 0 instant usually we draw, right? And thereafter we allow the system to move a time interval simple t. Suppose after time interval simple t, particle P is here. Right? Okay. Then here, particle P. Particle Q is now here. Right. We will draw the diagrams with me. Like this. It's particle Q. Okay. So we are given this is time equals t. Right. We are given this what? Show that the length x of the elastic string. Show that the length x of the elastic string. Length of the elastic string should be measured from O. Length should be measured from one end of a string, no? From one end of a string to other end is the length. So therefore, this x is at time t is measured from this O, like this. X. People, you know, if this is time t, the distance to the particle P from O is x. We know in differentiation, we said that location we mark people the acceleration as x double dot, velocity as x dot. Okay. That occasion, a tension creates in the elastic string, suppose that is T1, then this end also people T1, and a different tension acts in the inelastic string, suppose this is T2, this end also T2, this end T2, upwards T2, and this is the particle Q, the weight is mg. Okay, and people now here on this particle, the normal reaction and mg also acting. They are anyway not important to us for our discussion, so therefore usually we don't mark them. Though you mark them, never mind, but usually at the examination, no any question, those are not expected. Okay, now people, up to here you can understand. But the first thing, t equals 0 instant, you draw the diagram. And allowing the system to move a time interval simple t, draw that diagram. And at time equals t instant, people, definitely this way, a distance to the particle that moves under simple harmonic motion should be measured from a point. Right? The distance, simple x at time t from a fixed point to the particle that moves under simple harmonic motion, you have to mark in that diagram. Okay. Now people, the next thing is at t equals t, this diagram for the particles, we apply f equals ma. We apply f equals ma. Therefore, f equals ma equation we apply at what occasion? T equals t occasion. Right. Now, other thing is this. When this particle P moves with acceleration x double dot, since this string is inextensible, you know the acceleration of this also x double dot. That's the obvious thing, no? That will obvious thing, no, right? The reason is, suppose now girl and boy are like this, move this way, this way, keeping like this, holding their hand. Okay, what can you say the velocity of this boy and the girl? What can you say about the acceleration of the girl and the boy? Can somebody answer? Can they be different? Equal. Somebody says equal. Somebody says equal. Because he knows this. Because he has the experience. Okay, good. They are equal people. Like that, the string is inextensible. Therefore, this velocity and acceleration of the particle p equal to this. Okay, the same acceleration, the same velocity. Right? Because this is inextensible, like this situation. Right? Okay. Now what we do is, first we find the tension in the elastic string by using this formula. Okay, right? It's x is people extension. Extension means what? The extra length given to the elastic string beyond its natural length, right? Then T1 you can write, people. T1 you can write what? T1 is, we are given the modulus of elasticity as mg. Modulus of elasticity as mg. Lambda is mg here. X is the extension. People, how to write extension? At the moment, the whole length is x. Natural length is a. Then extra length is x minus a. X minus a. Extension is x minus a. Divided by natural length is a. This is the tension in the elastic string. Okay. Now we apply, people, F equals ma for the particle p and the particle q both. Right? Now we apply in F equals ma number 1 for p. We apply this direction. What do you get there? T2 minus T1 equals m times x double dot, number 1. And here, secondly, for q downward, mg minus T2 people equals mx double dot, number 2. Right? We need to obtain, people, a relation this way, x double dot and x. Right? Now what we do is, I add this 1 and 2. Adding this 1 and 2. What happens? This and this will cancel off. Mg minus T1 is equal to 2mx double dot. Right? Substitute for this T1 by the answer this. Mg minus T1 is that mg upon a x minus a 2mx double dot. Cancel down this m, people. Right. Yeah. So then we can take minus g by a out. Minus g by a, when you take out, here we get x minus a. Here g by a means minus a coming. No, people? We have divided this by a and multiplied by a. No. Once you take this g by a with minus sign out, another minus a will be remaining there. Equals 2x double dot. Then you can subject this x double dot Like this. Therefore, x double dot is minus g upon 2a x minus 2a coming. Okay. Now, asking to take we'll take this left hand side. X double dot plus g upon 2a x minus 2a equals 0. The first answer we obtained. People, this answer you can very clearly see here. This answer, this one, if I consider, if I take this as our omega squared, this takes the form x double dot equals minus omega squared and expression in x. People, at the beginning I told you, soon after this constant, there can be what? A linear expression in x. We got that one. Not only x, sometimes instead of x, we get linear expression of x. That we got here, x minus 2a, right? Okay, now according to this, you can see this follows what, people? The characteristic equation of the simple harmonic motion. Therefore, by this equation, taking this to this side, people, after reaching here, this one means really this. This means the characteristic equation. So therefore, by this equation, similarly this, we can say the particle P performs in simple harmonic motion. Okay. That one we proved. Right now? Yeah, we are given. Right. Elastic spring satisfies equation this. Right. So then its omega mean what, people? Then here, this is omega squared. Right. This equation we obtained. Omega squared is that g by 2a, given omega root of g by 2a. Okay, right. Up to here we came. Right. Usually, people, the characteristic equation in the simple harmonic motion in any question usually asking to find. That we usually find, people. One method is apply F equals ma. There is another method, that is, people, using the conservation of energy. I said throughout the motion, no loss of energy, no. That also we can use. I'll discuss those kind of questions in the mid of the lesson. Right? Okay. Now first one is okay. Right. Now come to next part. Up to here you can very easily understand. Okay. Next part, people. Next part is this. If the solution of the above equation, people, now we know, suppose we need to find the center of the simple harmonic motion. How to find the center? People, I said in this characteristic equation, x double dot equals minus omega squared x. To find the center, after this constant, whatever you have, equate that to 0. Thereby, you can find the center. Or else, you know, at the center only, people, the acceleration is 0. Here the acceleration is this. If you bring this to 0, people, you can find this x value. Right? Or else in here, soon after this constant, what you have, once you equate that to 0, what do you get? X minus 2a equals 0. Then x equals 2a. X equals 2a. X is measured from O, people. Then x equals 2a is the position of the center. So therefore, people, in this simple harmonic motion of the particle P, the center is this edge, because this is a 2a is here. This is the edge. Right? This is the edge. That edge point is the center of the simple harmonic motion. Now, people, you know, the simple harmonic motion particle, that particle moves on either side of the center the same distance. That is called as amplitude. right? But in this case, the center is this. Then the particle P, once it comes to the center, particle P has the idea to continue the motion on the right hand side of the center. But people, according to this setup, the table ends from here. Then the particle P cannot completely describe what simple harmonic motion. It can describe the simple harmonic motion until it reaches to the center. So therefore, people, at the question, don't expect always but a complete simple harmonic motion also. We know a simple harmonic motion means what? A, O, A dash, O, A. Like that. That is the complete simple harmonic motion. That kind of motions, people, usually we won't get in questions. Very rarely a question coming like that. We get really in the question at the examination, you get a part of the simple harmonic motion. That also you have to keep in your mind. So otherwise, you might inquire, how can this complete simple harmonic motion occur here? No, people, not complete simple harmonic motion. Some occasions, part of that occasion occurs. Right? If you have this idea, people, you have particular feeling, flexible feeling, smooth feeling. Otherwise, you have some unnecessary issues, doubts in the mind. Then you can't work out the question, right? Okay, so therefore, always don't expect what complete simple harmonic motion in our question, right? Then here, in this case, once the particle P move in under simple harmonic motion to the edge is the center. Actually, the particle tries to complete the other part also under SHM, but it can't complete because after reaching this one, this particle is coming down, right? So particle moves under simple harmonic motion subject to this equation as long as the particle P moves on the horizontal table. When it comes to the vertical position, people, this motion no longer valid. Okay, right? Why, people? The F equals ma equation will change soon after this when the particle P comes to here, vertical position. So therefore, we don't discuss those parts up to the edge, the motion of P simple harmonic, that only we consider. Okay, right now. Now, the next thing is this. People, can you remember that we proved when we derived that equations, 3 equations we derived, no? It's the last one, the relation between displacement and time t. We obtain something like this. X equals a sine omega t plus b cos omega t. I think you can remember this. There I told you this x means what the x here we have in the characteristic equation. Like that, people, once I bring this to this side, we get this. Then soon after this constant, what do you have? That only come in here to the left hand side. Now, like that, people, this x minus 2a in the question itself given, this x minus 2a can be written as the form this. What form, people? X minus 2a equals a cos omega t plus b sin omega t. Correct? This right hand side can be written as this. Right? We expect this kind of solution. Why? We have proved for this kind of characteristic equation, this kind of solution we can write. This left hand side thing is soon after this the constant, what do you have? That is the one here we get. Here this omega, people, this like that. Here also we have omega. That should be, people, this. That also given in the question. Omega is root of g upon 2a. Then much easier. Now we'll see, people, after this what happens. Then I am going to write this solution of this equation is x minus 2a is equal to what? A cos omega t plus b sin omega t. Right. Okay. Right. Find constants a, b. Right. Find constant AB. People, finding the constant AB is again very easy part. Always, after getting this kind of equation, definitely there are two constants to find. Whenever you find people these two constants, we use what? At t equals 0. At t equals 0. At t equals 0 means people, when the system begins the simple harmonic motion. Remember people, there are some questions. Soon after releasing the system does not enter into the simple harmonic motion. The system moves in a separate motion, and after some time only, the system or the particle enters into simple harmonic motion. People remember, this equation is valid only for simple harmonic motion. So therefore, in this equation, t equals 0 mean at the very first instant, the simple harmonic motion begins. Understand? So therefore, whenever we use this equation to find this A and B people, A, B constants can be found by applying the conditions at t equals 0. At t equals 0 mean people, the very first instant, the particle enters into simple harmonic motion. You know people, in this case, the particle P enters into simple harmonic motion at this position. T equals 0 means this position, no? You know, at t equals 0, the distance to this particle P from O is what? A. That means x is A. X is the distance to the particle P from O. So therefore, we use the initial conditions. What? At t equals 0, first thing you can write is people, x is A. Correct, no? When the particle P is here, the distance to the particle P from O is A. That means x is A. Well, what is the other one? Other one is, people, when the particle P, when it begins a simple harmonic motion, its initial velocity 0. From rest only we release. Then particle P begins the simple harmonic motion with initial velocity 0. So therefore, at t equals 0, another data we have what? Velocity of the particle P is 0. What is the velocity? X dot 0. X dot 0. Now what we do is people this. First, for x we substitute A, t0. Then we get one equation involving A and B, or sometimes one answer. Secondly, people, since we need x dot, we differentiate both sides with respect to time t, and we get x dot, and we put that 0 with t equals 0. Thereby the two constants we can find. So therefore, always this kind of equation, to find out that unknown constants, people, we use the initial conditions. They are called as initial conditions. Initial conditions means people, t equals 0 conditions. T equals 0 means people, not the question begins, that in the sense the motion begins. T equals 0 means people, simple harmonic motion begins. That moment only t equals 0. Because for any other case before, this equation can't be used, because this equation is valid only for simple harmonic motion. Right. So now if I put x equals, say, t equals 0, I put x equals, say, a minus 2a. T equals 0 means here t is 0, cos 0. T into omega is 0, cos 0. Cos 0 is 1. 1 into a is a. And people, b, here when you put 0, sine 0 is 0. Therefore, we get really minus a equals capital A equals minus a. Right now, a equals minus a. We got one constant. Right? Now, to use the second condition, we should have velocity. To get the velocity, people, we can differentiate this with respect to time t. I take this as star. Right? I take this as star. Now I differentiate this star. Right? Differentiating star. People remember, we are doing now a past paper sum, right? Not in combined maths, earlier. Past paper sum we are doing, right? It's very easy, right? Okay. Now differentiating star. differentiating star with respect to time t. People tell me what is the first one? X derivative is x dot. 2a is a constant, 0 equals a is a constant. What is the derivative of people cos omega t? Minus sin omega t into omega, no? Minus, I write here, sin omega t into omega, this way. Right. This one. B is constant. Sin omega t is what? Cos omega t into what, people? Omega, no? Then b omega cos omega t. Right. Now we substitute, people, for x dot what? X dot is 0. Where? When t equals 0. X dot 0. T equals 0. When you put here, what do you get? Here we get 0, no? Sin 0, 0. This whole thing will be 0. B omega, right, people? Cos omega t. We can write, people, here. Omega t. T is 0, no? Then cos omega t is 1. Then we get b omega into 1 b omega. Right? B omega product 0. But, people, in the question we are given omega as this. Therefore, this omega not equal to 0. And this says, people, b should be 0. Otherwise, this product will not be equal to 0. B is 0. Now we found, people, a and b both. After knowing this a and b, people, we can put that a and b values in star. Now you can write. Now by star you can write, people, x minus 2a is equal to a is minus c cos omega t. B 0. When you put b 0, people, this whole thing will be 0. Then the relation between x and time t is this. I can subject x equals 2a, taking this right hand side, minus a cos omega t. This is the relation between x and time t, right? Right, people. Now take this up to here. What do you feel about the question? Nothing, no? It's very easy lesson. Very easy lesson. Right, people. Now what is asking next? Show that the particle P reaches to the edge after a time this much. Right. When the particle P reaches to the edge, people, you can see, people, when the particle P reaches to this edge, what happens? That occasion, this x will be equal to a. X will be equal to 2a. Right? When the particle P comes to the edge here, this x value, it is measured from over, right? X will be 2a. Once you put x is 2a here and find the corresponding t, that is the time taken by the particle P to move to the edge. Understand? Therefore, this equation now we can use for, people, to find time for this particle to complete particular journey. Okay. Then we can write the time. Write down the time particle P takes to reach. The time the particle P takes to reach the edge of the table. The edge of the table can be found by putting x equals 2a in the above relation. X equals 2a in the above relation. That is this. Put that. What do you get there, people? X is 2a equals 2a minus a cos omega t. 2a and 2a you can cancel down. then this gives us minus a cos omega t equals 0. This implies, people, cos omega t equals 0. People, can you tell me this cos omega t should be an angle, right? Then tell me for what angle this cos becomes 0? For what angle this cos becomes 0? 90. 270. 270, can't you take 270? People, now only that motion, simple harmonic motion and the corresponding circular motion we need. You can remember, people, you can remember, we said what? Every simple harmonic motion has a corresponding circular motion. This way. Suppose like this. The point Q moves on the x-axis under simple harmonic motion. Then the particle P or the point P moves on the circle as a circular motion. You can very clearly understand. After starting the motion of this Q, okay, suppose this Q passes this center O and comes somewhere here, right? That occasion, when the point Q comes to the point O, the particle or the point that moves on the circle coming to here, turning through the angle 90, pi by 2. If this Q passes the point Q, the center to the left, comes only, this angle will be going beyond 90. So then you can very clearly understand, people. The particle P, which moves in the simple harmonic motion, center is here, no? It is now reaching to the center. Like here Q. Once the Q reaches to center only, the angle is 90. If this particle Q that moves in simple harmonic motion passes the point O and come to the left of the center only, the angle will be more than 90. Then, people, we are actually considering the motion of the particle P until it reaches to the center, no? So therefore, due to any reason, that angle turned the particle that moves on the circle cannot exceed 90. So therefore, cos omega t equals 0, we don't write omega t as 270. No chance of what? Turning that angle by the point P which moves on the circle. So therefore, we take here omega t as 90, and not 90 we write pi by 2. Then we write here, people, omega t is pi by 2, and then t equals pi by 2 omega. Then you know that we are given, people, omega in the question as how? Omega given as, people, root of g upon 2a. Then we get pi by 2 times omega. Then we get, people, it's 2a by g root like this. And cancelling this and this, we get pi, right, a upon this a. This is the time. This is the time, right? This is the time. Therefore, particle P takes the time this much to reach the edge. Okay. With the velocity, that means, people, asking to find the velocity of the particle when it reaches this edge. Velocity means x dot. Now this relation we differentiate. Then we get x dot. We'll see what happens then. Differentiating what? X equals 2a minus a cos omega t. What do you get? X dot t equals 2a is a constant along 0. Minus a is a constant. Cos omega t derivative is equal minus sine omega t into omega. Therefore, x dot t is equal to a omega sine omega t. Yeah. Now, people, in order to find the velocity x dot, we have to substitute this t. People, what t we have to substitute there? That t is the time taken by the particle p to reach the edge. That is this. That t only, people, we have to substitute here. Omega is that answer given. Then, people, t we have to substitute here. People, here not only t, omega t, both we need. The t, this answer given by omega t pi by 2. So therefore, without substituting this t alone here, this value, we substitute for both omega and t product by the answer pi by 2. Because there we need omega t. Omega t answer is pi by 2. Then, people, rather than substituting this one and omega separately, the directly answer we can obtain. But for this omega, we substitute that given thing. X dot a omega, people, given as 2a by g root, no? G by 2a root. And sine omega t is pi by 2. Sine 90 is 1, people. Then we get the velocity what? A root, the answer is given how, people? Yeah, this root a we can cancel down with this a, then we get root a that we can put inside there. G a by 2 root g a by 2. This all, people. This all. This all.